Hi, this is Alex from devstories.eu. OpenCV Computer Vision Deep Dive, Episode 2 of 20. Applying a blur filter to a photo feels like a complex visual effect, but computationally, it is just replacing every single pixel with the mathematical average of its immediate neighbors. The mechanic behind this is what we cover today: convolution kernels, filtering, and edge detection. When you hear the word convolution, you might immediately think of convolutional neural networks. We need to separate those concepts right now. In a deep learning network, a model figures out the values inside its filters during a massive training process. Today, we are talking about classical two-dimensional convolution. These kernels are fixed, hard-coded mathematical matrices that have existed for decades. They do not learn, they just calculate. A kernel is simply a tiny grid of numbers. A common size is a 3 by 3 square. Convolution is the process of taking this tiny grid and sliding it across your entire image, one pixel at a time. At each stop, you align the center of your kernel with a specific pixel in the image. Then, you multiply each number in your kernel by the value of the image pixel directly underneath it. Add all 9 of those results together, and that final sum becomes the new single value for the center pixel in your output image. You do this for every pixel. The numbers you put inside that small grid dictate exactly what happens to the entire image. If you fill the kernel with fractions that add up to 1, you get a blur. A Gaussian blur is a specific type of kernel where the center value carries the most weight, and the values taper off as you move toward the edges of the grid. This creates a localized weighted average. This is the part that matters. We do not blur images to make them look artistic. We blur them to destroy noise. A camera sensor records tiny, random fluctuations in light. If you try to analyze the rigid structure of an image with that static present, your algorithms will fail. Gaussian blur smooths out the erratic noise while preserving the general shapes. Once the noise is gone, you usually want to find the actual objects in the frame. Consider a camera system designed to read license plates. Before you can read the characters, you have to isolate the rectangular plate against the car bumper. To a computer, an edge is simply a sudden transition from dark pixels to light pixels or vice versa. To find these sharp transitions, we swap out the blur matrix for an edge detection matrix, like the Sobel kernel. A vertical Sobel kernel is designed specifically to find vertical edges. It's a 3 by 3 grid containing a column of negative numbers on the left, a column of zeros down the middle, and a column of positive numbers on the right. As this kernel slides across an area of solid color, like a smooth gray bumper, the negative and positive numbers multiply against the same gray value. They cancel each other out. The sum is 0, which translates to a block pixel in your output image. Solid areas disappear. But when the kernel lands right on the vertical boundary between that dark bumper and a bright white license plate, the math changes. The negative numbers multiply against dark pixels, producing a small value. The positive numbers multiply against bright white pixels, producing a massive value. They no longer cancel out. The final sum is a very high positive number, which creates a bright white pixel in your output image exactly where the edge is located. You just turned raw color data into structural geometry. The core takeaway is that a classical convolution kernel is nothing more than a local mathematical rule applied globally, dictating how every single pixel should react to its immediate neighbors. Thanks for spending a few minutes with me. Until next time, take it easy.